Welcome back, everyone, to MATA35. This is going to be the lecture 2B. So the lecture numbering is going to be a little bit odd because I sort of have things ordered in my head by each week, and so there's lectures A, B, and C within each week. And sometimes you might, if we get ahead, if we get ahead of the material in this class, we might start going into lecture 3A, and even in today's lecture. But this organization will hopefully match the syllabus and the course calendar. The first things first, I know many of you are going to have questions about the quiz, since I just gave you the practice quiz. Let me show that right now. So I just gave you the practice quiz over late last night, and you'll notice that there are a lot of problems. And this is because I've sort of described many of the basic integration techniques as sort of like multiplication tables. You really need to be able to know them and do them quickly. So there are problem one is going to be a series of 10 super fast integration problems. Ideally, you should be able to, most of these problems you should be able to look at and almost immediately know the answer, because all you're doing is you're applying some formula. So like, for example, the integral of 5 dx is just 5x plus c. And that should be immediate. We also have some other harder problems, so let me skip problem 2 for now, but we also have 2 word problems, and there will be exactly 2 word problems worth the same amount of points on your actual quizzes. One of them will involve numerical integration, so there will be a couple of different steps where I expect you to use something like Riemann sums or the trapezoid rule. And there will be a problem that's just a more general word problem where you have to do an integration to do it. And so note that these 2 problems are both worth 15 points each. Each of these sub-problems of problem 2 is worth 8 points each, and these are a lot harder. So many of these are going to have to use integration by parts or substitution or make use of some more complicated ideas from definite integrals. Note that you may leave answers in terms of e, log, sine, square root, etc. I don't expect you to convert to decimal. You are not allowed to use a calculator, so unless you have memorized your log tables, which I know I certainly don't, you would find it very difficult to give the answers in decimal. So you don't need to do that. You may leave them in terms of, you should still simplify as much as possible, but only simplify as much as you can without needing to, well, use a calculator. Where is this posted? Oh, this was on the, did you guys not get the message? So there was a message that was sent out last night. So let me drop it in chat, actually. Yeah, it was in the announcements. But here's the practice quiz. So I just dropped a link in the chat. So it's under the announcements, under emails. So hopefully you guys all get those. If you don't, you should make sure your spam filters are set correctly, because I will be using that for announcements. Most things I will also put on the course website. I guess I haven't put the practice quiz on the course website yet, but I will do that later. Okay, so does anyone have any questions about the quiz before we get started with today's material? Okay, so let's go look at the course calendar again. Oh, one other thing I should mention. This coming weekend is a long weekend, so we have no Friday lecture because it is a presidential day. Note that you guys also, I think, have a holiday on Monday, but that isn't applicable for this course because this class is a Wednesday-Thursday class. Okay, I think that's enough logistics. Let's go ahead and get started with the course proper. Let me switch back over to my PowerPoint, and let's get started. So, today we're going to be talking about, excuse me. Today we're going to be talking about volumes and improper integration. So, let's start with volumes. So, what's a volume of a simple solid? Well, that's pretty easy, right? So let's say we start with a cube with side length s. Well, we all know how to compute the volume of this cube. This is just volume is equal to s cubed. Now, there are some other figures that we also know how to compute volumes for. For example, if we have this rectangular block. Oh, let me see if I can draw this properly. Come on. There. So if we have a rectangular block with 2 side lengths s and s and a length l, well, this rectangular block has volume s squared times l, because we have the area of the face here times the length. Let's see, let's put that in blue. Okay? So we can make use of that idea and get areas of some things that aren't entirely rectangular. For example, one common one that's super useful is a cylinder. Pretend the bottom layer is a circle. So here we might have some radius r, and we have some height h. And so for the cylinder, we know that the volume is equal to, well, pi r squared, because that's the area of the base, times the height, which is going to be, let's do that in black, which is going to be h. So this is the height times height. Okay, so that's all well and good. But now, what if we have a more complicated shape? Let me see. Let's say we have a vase. So if we have a vase here, so it has a circular bottom, and let's say it's circular everywhere, since this is an example of pottery. Let's see. How much volume does that vase contain? Well, now, this is a little bit harder, right? Because you can't just look at the height or the area of each individual area, the area of each slice, or maybe you can. So now, before we move forward, I'm going to go ahead and ask another silly question, just to give you guys a bit of a hint of something, just to give you guys an opportunity to reply and make sure you all are awake. When do you guys think pottery was invented? So we're getting a lot of A's. So before 1 AD, does anyone think it was more recent? Okay, so we're getting a lot of A's, a few B's. Come on, why is my thing not updating? Ah, there. Okay, and you guys are correct. So the invention of pottery was actually nearly 20,000 years ago, and there are some pottery fragments that people have found in a cave in China, in the Xianrandong in China. And so pottery actually even predates agriculture. So now, we've been making these bases for 20,000 years, but how do we actually compute the area? Well, in practice, you might say, well, you fill it up with water, and then you know how much how much volume it contains. And that is a very good practical answer. But we're mathematicians in this room right now. I know you guys are biologists, but we're in a math class. And so let's try to solve this by using calculus. And this will be useful sometimes because if you have a vase and you break it into a bunch of pieces, well, maybe then you can't fill it up with water anymore, but you still want to know how much water the vase could have contained. And for that, you might have to take each piece and then simulate having the entire pot again, and that will tell you how much volume that the vase could have contained. And so these are examples of solid revolution. So for solid revolution, so let's recall that the area under a curve can be approximated by rectangles. So the A was the limit as n goes to infinity of some Riemann sum. So this is something we covered in class. Wait a moment, where did my animations go? Sorry, my animations are in the wrong order. But, okay, so we can draw our Riemann sums. And here I've drawn them along the vertical axis. It doesn't matter, so we're integrating along the vertical axis instead of the horizontal one, but it's still the same sort of idea, right? If you want to divide up that area, you can divide it up into the area to the right of the curve and break it up into little rectangles. And of course, we have a notation for this, which is the limit as from a to b of f of x dx. But now, what if we want to rotate about the vertical axis? What is the volume? Now, what we can do is, if we have our figure here, we can rotate it around the vertical axis, and then we get something that's vaguely pot-shaped. So these are things called solids of revolution because we've revolved around it. then what we can do is, instead of dividing up into these rectangles, we can divide it up into a bunch of little cylinders. And once we've divided it up into all these little cylinders, we can compute the volume by just taking the limit as our cylinders go from 1 to n as you get smaller and as you get thinner and thinner cylinders. Because we know how to compute the area of a cylinder, right? So if we look... Yes, what's the question? Okay. So this is super important. So for those of you who didn't hear the question is basically, why do we have a limit here and then we have a sum? And so this goes back to how we're defining the Riemann sum. So we have both of those things there. And the question is, why do we have a limit and a sum? And the answer to this is, when you're doing the summation, if n is an integer, well, it's some finite number of rectangles, right? So when we're dealing with this in the context of a numerical simulation, like with a computer, you actually only sum up a finite number of numbers because, well, computers are finite. You can't sum to infinity. But now, when we're working with calculus, the whole point is that we have access to infinity through these things called limits. And you could also think of this as the sum from 1 to infinity of f of xi delta x. But that isn't quite as precise. And so instead we write it as the limit from n goes to infinity of the sum from 1 to n. Because what you're saying is that the different points. So you might first try going from 1 to 100, and then 1 to 1,000, and then 1 to 10,000, and each time you're getting closer and closer to the number that we've defined by this limit. And it turns out that when you do this as n goes to infinity, so when you have infinitely many tiny little slices, you actually get the area underneath the curve without any error. Can we use this method for only symmetrical objects? We had a question in the chat. The answer to that for this rotation method is yes. They have to be rotationally symmetric, which is why I gave the example of pottery. Because what you're doing is you're basically dividing it up into lots of little cylinders, and that only makes sense if you can approximate each of the different layers as a tiny cylinder. Let me go ahead and write a couple more of these things, which I was going for. So, because each of these little cylinders, we know how to compute the area of each of these little slices. Or sorry, know how to compute the volume of each of these little slices. Because we have a radius r, and this r is going to be equal to f of x sub I. Because our, and then each of these little chunks is going to be of height delta x. And so once you've done this, what you get is that this is the integral from a to b of pi times f of x squared dx. Yeah, so here we're assuming the vertical axis is the x-axis. I drew it this way just because it's a little bit easier to see the rotation this way. You could also think of a rotation around the horizontal axis, or any axis for that matter. So these are solids of revolution. There are a couple things you have to be careful of. One is that you do need your curve to be always on one side of the axis. Otherwise, your rotation ends up giving you a weird figure, and you have to deal with negative integrals. But yeah, so the basic idea here is that if you have something that you are forming by this sort of revolution, meaning that the area, the volume is captured by these cylindrical slices, then you can use this idea of this integral of pi f of x squared dx in order to compute the volume. Okay, we had quite a few questions. Are there any more here? Where did the delta x go in the bottom equation? Well, this is one of the standard things that happens when we pass to the limit. So if you look here, the delta x turned into a dx. And if you look here, the delta x turned into dx. This is just, one way of thinking about it is that this summation notation of the dx is a infinitesimally tiny slice. Delta x is a finite slice. Dx is an infinitesimally tiny slice. And so as your limit goes to infinity, your delta x becomes dx, and your summation going from 1 to infinity becomes this integral, this continuous thing. So a lot of what happens with integral calculus is you're passing from an infinite number of you're passing from finite slices to infinite slices. And when you do that, you pass from discrete summation to this continuous integration. In fact, if you go back to the history of like why we use this weird squiggly S symbol, it's because people originally wanted it to also represent summation. So the squiggly S symbol actually means summation in some sense, even just like the big sum symbol does, the sigma does. So they both mean summation, just one means discrete summation, and another means this continuous integration. Okay, but let's see another example, and hopefully this will become a little bit more clear. So, how do we compute the volume of a sphere? So now you can sort of think of a sphere as a solid of revolution, right? So what are we revolving? Well, there are a couple ways you could do this. I'm going to revolve around the x-axis, so let me revolve around the horizontal axis this time. And I'm going to have just draw a circle of radius r. Or a half circle of radius r, because what we're going to do is we're going to revolve this half circle around the x-axis. So now it's important to know what the different f of x here is. And to do that, well, let's use the equation for a circle of radius r. That's x squared plus y squared is equal to r squared. And so then, therefore, y squared is equal to the square root of, y is equal to the square root of r squared minus x squared. And so this is our f of x function. Okay? If you had we're taking a square root. If you had the minus, you'd have the other half of the circle. But we only want the top half of the circle because we want the area between the top half of the circle and the x-axis. And then we're going to revolve that around the x-axis to get our sphere. So now, what happens when we do this? Well, in order to do this, we need to take the integral from minus r to r of, well, what was our formula? Pi times f of x squared dx. Now, one of the other things to notice is that this example is actually symmetric in a very nice way. And so what's on the left side of the y-axis and the right side of the y-axis, those have the same volume because the circle is, well, symmetric in all sorts of ways. And so what we can do is we can set this equal to twice just the integral from 0 to r. And we know this because the two sides have equivalent volume. And then what was pi r squared? So let's move the pi out in front. What was f of x squared? Well, that's just r squared minus x squared. Squared dx. And so therefore, this is equal to 2 pi times, well, what is this integral? This is r squared x minus 1/3 of x cubed from 0 to r. We plug this in, you get 2 pi times r cubed minus 1/3 r cubed. Because note that when you plug in x is equal to 0, the entire equation, everything in the brackets goes to 0. And so this is equal to 2 pi times 2/3 times r cubed, which is equal to 4/3 pi r cubed. Okay, and those of you might remember that, let's see, there was a question, where did the square root go? So let's go repeat there. So note that f of x here is equal to the square root of r squared minus x squared, right? But we're taking the square of that. And so when you take the square of the square root disappears. And so that's why you have this r squared minus x squared there. Yep. Okay, so this is one way that you can compute the volume of a sphere. Let's give another example. So let's suppose that we wanted to compute the volume of a cone. So this is obviously also a volume of revolution. Here we're integrating around we're revolving around this vertical axis. Let me rewrite it actually, just to make the point that you can revolve around any of these axes. So I'm going to rewrite this and draw this around the x-axis. So there's x, there's y, and let me do this in blue. So Okay, so one of the things you can do is you can see that I've turned this cone on its side so that it matches along with the x-axis. It's a little bit hard to draw, but what we're seeing here is that then what we can do is when we see that the area underneath between this line, so this line here, which is just the y is equal to r over h times x line, and you can see that this is the line that'll give you precisely, this figure is precisely the same as that figure. Once you've done the transformation. And then what we can do is now we have this particular equation. Now all we have to do is revolve the area underneath the y equal r over h times x line around the x-axis, and we'll get the volume of this cone. So let's do that. So then the integral from 0 to h of pi times r over h times x squared dx, because that is your f of x function, and you're squaring it here. Well, this is equal to pi r squared over h squared, if you move all the constants out in front of the integral, times the integral from 0 to h of x squared dx. We all know how to do this, so this is pi r squared over h squared times 1 over 1/3 x cubed from 0 to h. The 0 goes to 0, and therefore this entire thing is equal to 1/3 times pi r squared h. And that is the volume inside of a cone. Okay, so now, per usual, I'm going to have you guys try it out. So what we're going to have is I will ask you to try out the volume of the solid revolution generated by rotating the area underneath the graph of y equal to square root of x from x is equal to 1 from 0 to 1. And then I'm going to ask you what that's equal to. Okay? Could you go black for a second? Yes. Okay, so what we're going to do is we're going to do it for this y is equal to the square root of x from x is equal to 0 to 1. And let me go ahead and give you the formula again, just so that you guys have it, since it's not on this page. So the volume is going to be equal to the integral from a to b of pi times f of x squared dx. So hopefully this is enough information, and wait, why is my chat not resetting? Come on, reset chat. And I have a couple options here. And so what we're doing is we're taking this shape and we're rotating it around. Okay, so we're starting to get some replies. It looks like people are getting B. And yes, so this is actually just an application of the formula. So now that we've given you the formula, this shouldn't be too difficult. So this is an integral from 0 to 1 of pi times the square root of x squared dx. But the square root of x squared is just x, right? Or rather, it's the absolute, yeah, so it's just x. Let's the square integral from 0 to 1 of pi x dx, which is going to be equal to pi times 1/2 x squared from 0 to 1, which is just pi over 2. So the answer was B here. And it looks like people were able to get that correct. So, yeah, so well done. Now, someone asked in chat earlier, well, this only works for things that are cylindrically symmetric, right? So things that you're rotating around an axis, so like a vase. But it's not particularly helpful for things that aren't solids of revolution. Now, what can we do for these other volume integrals? So here what we were doing is we were integrating disk volumes around an axis, right? So we broke up our integral into a bunch of these little disks, and we said that the area of each of those was pi r squared delta x. And that's the reason we could take this integration. So this was equal to the integral of pi f of x squared dx. What about other shapes? Well, for example, what if we could break up our figure into a bunch of little squares? So maybe that's a little bit less obvious that you can do that. But the answer is, so long as what we're doing is, all we're doing is we're integrating this area times this delta x. And so if you think of the area function as just some other function, you can think of each slice as just multiplying by that area. It doesn't actually matter what shape it is, so long as you know the area of each slice. And so if you know, whoops. So if you know the area of each slice, then all you have is you have the integral of a of x dx. And so really this makes sense, right? Because if area is something like in meters squared, and you want to know volume, well, you just integrate it against another dimension, and so long as the function, your integral function is, your area function is correct, that'll give you the volume, because that'll be in things like meters cubed. Let's give you an example. So suppose that the vertical cross-section of a pyramid 100 meters tall is always a square. So we have a square pyramid here. So think of like the Pyramid of Giza, the Grand Pyramid of Giza. And suppose that this, oh sorry, could you go back for a second? Yes, let me go back for a second. Yeah, so the basic idea is if you're integrating something and you know that, and you can figure out what the area is of each slice, as you're moving down through the figure in any axis, you don't actually have to be an axis of revolution if you can figure out the area. Obviously, it's easier if you can figure out the area because it's easier when you have a solid revolution because then the area is just pi r squared. But in the case where you have some general figure, you may not know that the area is pi r squared, but so long as you do know what the area is, you can still do this integration by just taking the integral of ax dx. Okay, so let's go ahead here. So we want to know the volume of a pyramid. Well, this is a little bit trickier, right? Because you need to know what the area of each slice is. But those are just squares. And so all you need to do is you need to know the side length of the square. And we know that, which is 100 minus x meters, where x is the height above ground in meters. So that means we have an area function, a of x is just 100 minus x squared. There's no pi here because we're not revolving, we just have an actual square. And therefore, we know that the volume is equal to the integral for x equals 0 to x equals 100, since that's the height above ground, of 100 minus x squared dx. And there are a couple ways of doing this. You can do this directly. I'm going to use a u substitution just because that makes life a little bit easier. So I'm going to let u be equal to 100 minus x. So then du is going to be equal to minus dx. And once we've done this, we can substitute this in. This is the integral of, so let's see, this is u squared. And the du is minus dx, so this is minus u squared dx for u equal to 100 to u equal to 0. Now, one of the fun facts about definite integrals is if you swap the limits, then what you're doing is you're multiplying it by negative. So you get rid of the negative sign. Oh, sorry, that's a du, not a dx. du. There's a reason for this, and it's pretty easy to see this from the fundamental theorem of calculus, since the integral from if the integral from a to b of f of x dx is equal to some function f of some antiderivative f of b minus f of a, well, this is clearly equal to minus f of a minus f of b, which is equal to let me erase that. Which is equal to minus the integral from b to a of f of x dx. So when you swap the limits of a and b, you end up getting the negative of the integral. Okay, so now that we've done that, this is relatively straightforward to compute. So this is 1/3 u cubed from u equal to 0 to u equal 100, which is equal to 1/3 times 100 cubed, which is about 333,333 meters cubed. Okay, and so the point here is that the whole point of the solid revolutions is that we knew what the area of each of the circular slices was. If you have any way of figuring out that area, all you have to do is integrate that area, and you end up getting a volume. So so that was volume. What about something like surface area? Okay, so we knew how to get the volume of this cylinder. What about the surface area, not including the base? So remember, we had a volume which was equal to the integral from 0 to h of pi times f of x squared dx. So what about surface area? Surface area, not including base. So one idea that you might have is you might ask, well, what if we take this equal to the integral from 0 to h of 2 pi r, since that's the circumference, right? So if you were to integrate that circumference around, well, maybe you'd end up getting the surface area, f of x dx. So let me reset my polling here. What do you guys think the answer is? True, false, or question marks or exclamations? So if the area of a circle is pi r squared and the length of the perimeter is 2 pi r, can you just take the integral over the different perimeters, and that will give you the surface area? Because you're still integrating, the dimensions work out, right? Okay, so it looks like I wasn't able to trick most of you. It turns out that this does not work. So this does not work. You can get the correct surface area. So the correct surface area, there is a formula for this, and that's going to be equal to the integral from 0 to h of 2 pi times f of x times the square root of 1 plus the derivative d dx of f of x squared dx. Now, in many other calculus classes, this would be something that I would expect you to learn how to do. In this calculus class, we are not going to be talking about surface area, so you don't have to memorize. So don't bother memorizing this formula. It is not necessary. But I'm just giving you this example because I want to point out that using disks does not work for surface area because you're incorrectly approximating the paths. And simply because you can do an infinite integral of a bunch of infinite summation of a bunch of things doesn't mean it's a good approximation. So you need to be a bit careful because in this class I've been giving you a bunch of good approximations. It turns out there are a bunch of bad approximations as well. And the heart of the matter here is if you have a path, let's say we had a path of like this, a straight line path. If you can't actually integrate the path length by using rectangles. So it doesn't, if you use rectangles to integrate the path length, then that will be wrong no matter how many rectangles you do. Even if you do lots of tiny rectangles, it will still not get you a good approximation of the path length. And for this reason, when you're doing this surface area integral, you have to take into account the slope of each of the little cylinders. You can't just use a Riemann sum-like thing of like getting rid of all of them. So this is just a cautionary tale because you can't always do the sort of weird integration trick where you're just breaking it up into lots of little pieces. You need to make sure that the little pieces you break it up into are actually a good approximation. And in this course, we're not going to deal with how you think about what are good approximations. We're just going to give you some series of approximations. But if you ever do encounter this in real life, be really careful whenever you're trying to come up with an integration rule. And I think that is actually all of this part of the lecture. So this is all of volume, so this is all of the lecture on volume, oh wait, sorry. This is all the volume integration. This is not improper integration, that is in the next set of slides. But since that's another set of slides, I'm going to give you guys a 5-minute break while I set up for the new set of slides. So please be back at around 12:50, and we have another set of slides for the improper integration.